Now that we've introduced the idea of impulse, we can use force time graphs to get a better picture of what those look like. So by the end of today, we should be able to kind of redefine impulse. We've already kind of talked about it, but we want to look at it in terms of the graphical part of it. And we also want to be able to use a force time graph to determine the impulse delivered to an object. Those big questions are going to be, what is impulse? And how can you determine the impulse of an object using a force time graph? Remember, Newton's first law says that an object will keep doing what it's doing until its forces become unbalanced. So in order to change an object's motion, we need to apply some new force for a period of time. So if we have an object just sitting there, we need to come along and apply a certain amount of force to get it to move. If the object is already moving, we can change that motion by applying a new force. So in order to change an object's motion, we have to apply a new force against its motion for a given period of time. Newton's second law specifically describes how the motion will change when we apply that new force. Remember that anytime we have a change in motion, we call that an acceleration. There are three things that can happen when an object changes its motion. The object can speed up, it can slow down, or can change its direction. So those three things are considered an acceleration. Those three things are how a net force can change an object's motion. Now, how much the motion changes, or the amount of acceleration, depends on two things: the net force that is applied and the mass of the object. The more net force that is applied, the more the object changes its motion. The less net force that is applied, the less the acceleration. The acceleration also depends on the mass. We saw this with Newton's first law as well. The more mass, or the more inertia, an object has, the harder it is to change its motion. So the more mass, the more inertia, and the less acceleration. So in order to change the motion of a higher mass object, we would need to apply more net force. The other important part of these interactions is the amount of time that the force is applied. And this is what we mean by the impulse. So we're taking all of the force that is applied during that interaction and the amount of time that is describing the impulse. We can represent the impulse using a force time graph. This is simply a picture of the amount of force being applied over a given time, which is the impulse. So compare the two graphs here. Both forces are being applied for the same amount of time, but the one on the left has more force being applied. So which one do you think have the greater impulse? Just like with our velocity time graphs, we were able to find displacement of an object using the area between the line and the axis. On a force time graph, we can use it to find the impulse. So if we look at the area of the first graph, it forms a rectangle. That rectangle represents the magnitude of the impulse. How does this area compare to the second graph? The impulse lasts for 10 seconds in both situations, but there is more force being applied during those 10 seconds in the graph on the left. Since the area of the left force time graph is larger than the area of the right, that means that the impulse is larger as well. So let's look at these two graphs. Which one do you think shows the greater impulse? The graph on the left has a 10 Newton force. The graph on the right has a 10 Newton force. The graph on the left has an impulse time of 10 seconds, but the graph on the right has one that's less than 10 seconds. So just looking at those two graphs, we can see that the area of that particular rectangle on the left is going to be greater than the one on the right. So it is going to have a greater impulse. Now, what about these two? If we look at the graph on the left and the graph on the right, they both have an impulse time of 10 seconds. But the graph on the right has a force of 7 newtons, while the one on the left has a force of 10 newtons. That would mean that the graph on the left has a greater impulse. So what are we actually doing here? When we find the area under the graph, we are actually multiplying the force being applied times the time. This lets us write in a mathematical equation for impulse. In this equation, force is the force that is being applied, and we are going to measure that in newtons. T is time, and it's measured in seconds. Impulse is represented with a J. Nobody really knows why. So the impulse is just going to be the average force in newtons times the time in seconds. Since we are multiplying force times time, we get a label of Newton seconds. Be really careful with this one. This is not newtons per second, but newtons times seconds. So something to keep in mind is that forces acting on an object are not usually constant. Take this graph. Say we are pushing a box across a floor. The magnitude of the force changes over time. In the first 2 seconds, the force is increasing from 0 to 2 newtons. There's a constant 2 Newton force for 3 seconds after that, and then the force decreases down to 0 in the last 3 seconds. How could we go about finding the impulse on this box? Well, we know that the area under the line is going to represent the impulse. And we can take this area between the line and the axis and break it down into pieces. So take the first 2 seconds. What do we have here? The area between the line and the axis forms a triangle. How do you find the area of a triangle? Well, it's height times width divided by 2. The height on our graph turns out to be 2 newtons. The width on our graph is going to be 2 seconds. So we're going to take that 2, we're going to multiply it by 2, and then we're going to divide it by 2 because it's a triangle. So 2 seconds times 2 newtons, and take the half of that, it's going to be 2 Newton seconds. What about this next section of the graph between 2 and 5 seconds? This is a constant force of 2 newtons acting for 3 seconds. The area between the line and the axis forms a rectangle, so we will not need to divide by 2 to find this area. So here, the impulse is just going to be those 3 newtons times 2 seconds, and we find an impulse of 6 Newton seconds. Now this last section again has a changing force, so the area between the graph and the axis is going to form a triangle. The base of the triangle is 3 seconds, while the height is 2 newtons. Oh, there it is, 2 newtons. So it's a triangle, so we're going to take that 2 newtons times our 3 seconds and divide it by 2. So 3 times 2 is going to be 6 Newton seconds. Divide that in half for a total of 3 Newton seconds for that last triangle. So to find the total impulse of this interaction, we are going to add all of these together, and we're going to find a total impulse of 11 Newton seconds. All right, now that you've gone through that, can you define impulse? And can you use a force time graph to determine the impulse delivered to an object?